In this video, we're going to define vector spaces and subspaces. So let's start out with what a vector space is. What a vector space is it has two operations, which is addition, vector addition in this case, and scalar multiplication. Then if that's true, we're going to have those two operations, and it's a vector space over the complex numbers if the following 10 properties hold. That if I have u and v, which are elements of the little v, being elements of my vector space, then I should be able to add those two and it'll also stay within my vector space. And we call that closure. We have addition closure, the additive closure. We have some scalar multiple alpha, which it belongs to the complex numbers, and our u, which is some vector in v. Then if I multiply my scalar and my vector, it will also still belong in my vector space. We have the commutative property, which means I have two vectors, u and v, in the vector space v. Then it doesn't matter if I do u plus v or v plus u. So I'm not talking about closure, it's just going to have that equality there. We also have the additive associativity, which is you have u, v, and w all belong into the vector space. Then I can add v and w first and then add that answer to u. Or I can add u plus v and then add that answer to w. We also have to have the zero vector. And the zero vector is a vector such that when I add it to u, I'm going to get u for every u that I have in my vector space. I also have the additive inverse, which is, basically what we'd expect it to be, is that u belongs to the vector space. The negative u also has to belong to the vector space, so that when I do u plus the negative u, the additive inverse of u, that it's going to give me the zero vector. I should have scalar multiplication that is associative, so a and b, or alpha and beta, are two elements of the complex numbers, where u is an element of my vector space. Then it won't matter if I do my vector and my scalar beta and u first, and then multiply that by the scalar alpha, or if I multiply those two scalars first and then multiply it by my vector. We also should have the distributive property, which means if I have, and it's a cross vector addition, and we're talking about a scalar distributive property over vector addition. So alpha, again, is an element of the complex numbers. U and v are elements of the vector space. Then I have alpha, and I can do alpha, multiply the vectors, multiply the alpha after I've added the two vectors, or I can do alpha by each vector individually and then add those two results. We also have the distributive property of scalar addition. That means, I have alpha and beta are in the complex numbers. U is in the vector space, and then I can add my two scalars first and then multiply it by my vector, or I can multiply my vector by alpha and then my vector by beta and then add those two answers together. And of course, we have the one. If u is an element of the vector space, and we have this 1, so that when I multiply it by u, my vector u, that is still just my vector u. So I want to just say a couple of things here that we've been spending so much time in vector spaces or vectors, but when we're talking about vector spaces, we can have anything as the elements of those vector spaces. So it doesn't have to be a vector when we're talking about a vector space. I just want to make that clear. We're not really talking about a set of vectors when we're talking about a vector space. It could be something else. And when we talk about an axiom, that's just a self-evident truth. It's something that we all agreed on without any kind of proof. So when you see that word axiom, that means we all agree that 2 plus 2 is 4. And the real numbers 2 plus 2 is 4. That's what we all agree on. Now, where we are right now is we've been working on column vectors of length m, and we have considered plus and the multiplication as vector addition and vector multiplication of scalars. Where we are going is we're going to consider vector spaces that may be matrices or polynomials or functions or any number set like the complex numbers or the real numbers. And our plus may be noted as this symbol, which means it may not be what we expect as just being addition. So it depends on what we have. We have to define it now. What does this mean? We have to define what it means to have addition. And our multiplication may be noted as this. That means that we're going to define what it means to be this multiplication. It may be something different than what we expect it to be. So be aware that the plus and the multiplication symbol now could be a plus with a around in a circle, or a multiplication symbol inside of a circle. And all that means is that I have to define what that symbol is going to represent in terms of my vector space. That's all it means. These are the things that we need. We need to have a vector space must be a set. Okay? So to have a vector space, it has to be a set of numbers, and it has to be non-empty. Closure of two operations, that means that we have to have the addition, or however we define this symbol, this operation, maybe addition of vectors or addition of matrices, and it has to have the second operation, and we may have it as a multiplication of matrices or multiplication of vectors. So we have to have a vector, which is a set, and then we have to have the closure of the two operations. So I have to have two operations and it has to be closed, which means when I perform these operations, my end result must also still be in my set, my vector set, my vector space. Okay? So let's take a look at an example where we're trying to determine if my complex vectors of size m, so in other words has m entries, is a vector space. So first of all, we have the set. It's a set of column vectors of size m whose entries come from the complex numbers. Check. We've got a set. I have to check for equality, and this allows me to make sure that u plus v is equal to v plus u. Entry-wise, two vectors are equal as defined as what we would expect with column vectors of equality. So we've already had that definition. Check. Our first operation, we're going to call it vector addition, and it's going to be defined as we expect column vector addition to be, so it's closed. Check. The second operation, which we're going to call scalar multiplication, is going to be defined as we expect column scalar multiplication to be, and it is also closed. Check. No worries there. So the vectors, the column vectors whose entries come from the complex numbers of size m is a vector space. Not surprised. We've already talked about that. We're like, oh, okay, we're just, this is happening and we're cool. Now we've shown that it truly is a vector space. Now let's look at all of the matrices of size mn, determining if that's a vector space. So first of all, I have to define the set. Do I have a set? Yep, it's the matrices of size mn whose entries come from the complex numbers. Equality-wise, entry-wise is what we expect with matrices, is it how we defined them as being matrix equivalent. So we need that to show that u plus v and v plus u are the same, and so that we have the equality. We're going to define our first operation, which is going to be just matrix addition, just exactly as we expect. It is closed, so check, got that one done. The second one operation, we're going to call it scalar multiplication, as defined by scalar multiplication as we expect of a matrix. It is also closed. Check. So some of these are like, yeah, why are we going through that? Well, because we can, and it's nice, easy setups to show that these are vector spaces. So let's look at something different that we haven't been looking at. So let's look at polynomials. So let's look at all polynomials of degree n or less. Is it a vector space? Well, first of all, it's a set of all polynomials of degree n or less, with x being used as a variable with coefficients that come from Cm. So in other words, they come from the complex numbers. So let's check for equality. Here's my polynomial where I have a leading coefficient of an and x to the n all the way down to a naught. And then here's my second polynomial where my leading coefficient is bn x to the n all the way down to b naught. This is true if and only if a sub I is equal to b sub I for all I between 0 and n, and we would expect that. We actually use that information when we're doing partial fraction decomposition in Calculus 2 or Pre-Calc 1. We use that equality of polynomials so that we can solve for the a, b, and c in our partial fraction decomposition. So then let's define what we have for our first operation. We're going to call it polynomial addition. And we're going to define it as adding basically my two polynomials together, which is equivalent to adding the coefficient on like terms. So an, bn plus xn plus an minus 1, bn minus 1, etc. And we know that this is going to produce a polynomial of degree n or less. So it is now closed under polynomial addition. Check. The second operation that we're going to look at is scalar multiplication of a polynomial, and we're going to define it as a scalar being multiplied by my polynomial. That scalar is multiplying by my coefficients, and so it's not changing the degree of the polynomial, which means that when I multiply by the scalar, whatever it may be, that my degree of my polynomial is going to be n or less. So it is closed under scalar multiplication. Check. So what that tells me is that this polynomial of degree n or less is a vector space. Now, we hadn't talked about this before. We've really been focusing in on the matrices and the vector, the column vectors. Well, guess what? Polynomials are a vector space because they react the way we expect. There are some useful properties in this section, and the useful properties in this section are these. If V is a vector space, then the zero vector is unique to that vector space. If V is a vector space, then for every element in V, the additive inverse is unique for each element. If V is a vector space, and for every element in V, then 0, how I've defined 0, is going to be multiplied as a zero scalar multiplied by my element in V will be the zero vector. If V is a vector space and my scalar multiple comes from the complex numbers, then my scalar multiplied by my zero vector is still 0 all day long. If V is a vector space and U is an element of the vector space, then we get negative U is equal to negative 1, which is just a scalar of U. And if V is a vector space and alpha is from the complex numbers, then if we have the alpha, which is the scalar, multiplied by my element in V is equal to the zero vector, either my alpha is equal to 0 or my vector, my element is equal to 0, or both. Okay, and so then let's go on to vector subspaces. So this is where we really start to look at what it means to be a space and a subspace. Now, we had subsets. We talked about that in our last video. This one are subspaces. Now we're going to really define what it means to be a subspace. Suppose V and W are two vector spaces that have identical definitions of what vector addition means and what scalar multiplication means. And now we're talking about vector space addition and scalar multiplication in that space. And W is a subset of V. W is a subset of V. Then W must be a subspace of V. So when we are going to test whether or not our subset is a subspace, then these three things must hold true. First of all, that my subset is not empty. That if I have some element within W and some element Y in W, they have two different elements that belong to W, and then how I defined my scalar addition has to hold and be closed, be a part of. So my X, which is an element of W, and my Y, which is an element of W, that when I add those two together with my scalar addition, however I define that, it also must be in W. And then, of course, my scalar multiplication, so X is from the complex, and that should be complex, so that is the complex numbers. And X is an element of W, and then how I define scalar multiplication within my vector space, my bigger vector space V, must also hold true and be closed in my subset W. If that's true, then W is a subspace. So let's go through some examples. So let's take a look at my first example. W is a subset of R3. That means I have vectors that have 3 entries, and those entries are real. And we're going to consist of vectors of the form A, B, and the last position is 0. A and B are elements of the real numbers with the usual operation of vector addition and scalar multiplication. Is W a subset of R3? So we have to check to make sure it's not empty. Well, since A and B are elements of the real numbers, that the W is not empty. We're going to check for vector addition. So we're going to say, let U be A sub 1, B sub 1, and V be A sub 2, B sub 2, then, which are both elements of W. Then U plus V would be the regular addition, which is A1 plus A2, B1 plus B2. It also is going, because these are real numbers, addition of real numbers is still going to be a real number, so we have closure for vector addition. Let's look to see if we have closure for scalar multiplication. So say C is just a number in the real number where it's a scalar. So I multiply C multiplied by my vector U. Then C is going to be A sub 1, and then C, B sub 1, and then of course 0. And so we have closure for scalar multiplication, check. That means W is a subspace of R3. It's a subspace. It's not going to span it, but it is a subspace. We'll get to spanning here momentarily. Let's take a look at an example here. Let's let V be equal to R2. So my set V is R2, which means it's all the vectors that have 2 entries. And let H be a subset of V consisting of all the points that are on the line for negative 4x plus 3y, which is equal to negative 12. Now remember, we're talking about vectors. Is H a subspace of V? Well, first of all, we have to check it's not empty. Since H is a subset of all the points on the line, then clearly H is not empty, so check. Now I want to check for scalar, for closure for addition. Now consider the points U, which are defined by the vector 3, 0, and V, which is defined by the vector 0, negative 4. These are just basically the x and y intercepts wrote in vector form, which are, of course, on that line. However, if I do U plus V, if I take these vectors U plus V, I'm going to get 3, 4, and that is not on the line. That vector is not on this line. So we fail. It doesn't close. We can go no further. However, because you just didn't want to stop, because this is so much fun, let's check for scalar multiplication. Let A, alpha, be 2. It's a real number. And U being, as I defined before, 3, 0, which is a point on this line. It's a vector whose end, the tip, is on this line. As before, I multiply 2 by my U, which is going to be 6, 0, which is not on that line. So now I'm definitely going to stop, and H is not a subspace of V. It may be a subset, but it is not a subspace of V. Take a look at a polynomial example. And these should be subscripted there. It should not be up here. Subscript there, not superscript. So let V be a subset of Pn, where V is a set of all polynomials of degree 2, exactly degree 2, of the form ax squared plus bx plus c, where a, b, c are real numbers with the usual operations of polynomial addition and scalar multiplication. Is V a subspace of Pn? And again, that should be down below, and it shouldn't be as a superscript. I don't know why I put it as a superscript. It should be Pn. Okay, so first we're going to check to make sure it's not empty. Yep, clearly it's not empty. Because A, B, C are elements of the real numbers, then my V, my subset, is not empty. So check. Let's go on to the scalar addition. Now remember, I can choose any A, B, or C, so let's let A be 2, B be 3, and C be 1 on my first U, my first polynomial, my first element, if you will, and V also being an element of my big V. So I have here, I just want to make this clear that U and this little v, U and this little v, that's a terrible V, are elements of the large V, just so that we're clear. My V is defined as negative 2x squared plus 3x plus 1. When I add these together, when I add U plus V, I get 6x. This is not a polynomial of degree 2. So we fail. We go no further. V is not a subspace of Pn. P, and I don't know why I did that, but there we go. And I wrote it twice, because I could. I just wanted you to know that it really wasn't a subspace. So then we start to pick up some more theorems. It says the null space of a matrix is a subspace. So you're wondering why before, why did we do the null space? Well, it's a subspace, which means we have closure for addition and scalar multiplication, and it's not empty. So suppose A is an M in a matrix, and the null space of A is a subspace of Cn. So as an example, consider this. We are in C5, in which I have 5 entries, and they all come from the complex numbers. And here's how I'm going to define my W. Notice that W is a set of all the solutions of the homogeneous system. So here's our connection with homogeneous systems. Before you're like, why do I care about that? Well, because of this. Here's a connection. We take all of these coefficients, we build this matrix, right? We define it as this, which means W is the null space of A, and by the previous theorem, W with no work is a subspace. Boom, shakalaka. We are happy. We move on. Life is delicious. Moving on to linear combinations and what that means. Well, not really much different than what we expect, really, because we've talked about linear combinations before. But now we're going to talk about in terms of a vector space. V is a vector space given that we have n vectors, u1 through un, and n scalars alpha 1 to alpha n. Then their linear combination is going to be the alphas multiplied by the u's. No surprise, we have seen this before. What does it look like in vector space? Well, in R3, that means I have vectors where I have 3 entries, and those entries are real numbers. Here's V1, which is 1, 2, and 1. V2, which is 1, 0, 2. And V3, as an example, is 1, 1, 0. Then the vector U, 2, 1, 5, it's a linear combination of all these if we can find these C's or alphas such that C1, V1 plus C2, V2 plus C3, V3 is equal to U. So we take an augment on, just like we did before, this first row right here, this first row right here come from this position, and this position. My second row right here come from this position, and this position. And then the third row come from this position, and this position. So in other words, what I have is the first column is the first vector, the second column is the second vector, the third column is the third vector, and of course we augment on our U. Doing the RREF, we end up with this solution here, which tells me my C sub 1 is equal to 1, my C sub 2 is equal to 2, and my C sub 3 is equal to negative 1, which gives us U is a linear combination. Cool. So we can form linear combinations of any vector space. So let's revisit what it means to be a span. So let's revisit the span. Suppose V is a vector space. Given a set of vectors where their span is defined by S, in other words, this S is the spanning set that produces all the linear combinations, which is the span, is a set of all possible linear combinations. Symbolically, this is what it would look like. And from that, we're going to get this span of a set as a subspace. Suppose V is a vector space. Given the set of vectors where this set is our spanning set is a subset of V, then their span is a subspace. Cool, huh? Starting to make those connections, I hope. Starting to make those connections. So let's look at P2. Again, we want to do P2 down here. I don't know why I keep doing that. I just freaking love that, I guess. So then here's my V1. Here's how I'm going to define V2, and then V3 and V4. Now I'm going to try to determine if U belongs to the spanning set. In other words, can I get U to be a part of the span? Can I use the spanning set to produce this vector, this polynomial? So we find a linear combination. So again, I have this is the U, but this is different. This one's kind of different. And so this is the entries of my first polynomial. So as I go across the top, these are all the coefficients of x squared of each one of my polynomials. So this is slightly different. The second row is all of the coefficients of my x, And then my third row comes from all of my constants in my polynomial right there. So these are all my constants, not to be confused with the linear combination that I'm going to do. So I strip off the coefficients 2, 1, 2, and that gives me my first column. 1, negative 2, so 1, negative 2, and 0 is my second column. 5, negative 5, and 2, so 5, negative 5, and 2 is my third column. And of course, negative 1, negative 3, and to negative 2 is my my fourth column. This last column is what I believe U to be, which is 1, 1, and 1. This should be 1, 1, and 1. And then I end up with this being my solution, which is right here. Being this is the augmented matrix, and we know that we have this pivot in the last column, we know the pivot in the last column means that we have a no solution, which means that U does not belong to the span. That means that S, which is the spanning set, there's no linear combination of my spanning set, which will produce U. So in general, to determine if a specific vector U belongs to the span S, we just investigate the consistency of the appropriate linear system. So here's an example of my polynomials. These are the outcomes from this section. If A is an n by n matrix, then the column space is automatically a subspace of C sub n if my entries come from C sub n, M. If my entries come from R, M, then that's true for Rm, so I should put that in blue. If A is an n by n matrix, where my row space of A will be a subspace of Cn, unless of course my entries come from the real numbers, and then that would be C sub n. If A is an n by n matrix and the left null space, it will be a subspace of C sub m, unless of course I am talking about in the real numbers, and then it'd be C sub n. Anyways, that's it for this section. So let me know if you have questions on the homework, and we will see you in class.